specific topic, I mean, you can do it. Okay, so why is this an important question to the initial question? Why is it important to the initial question? Do you understand why Big Bang theory and inflation theory makes the initial question nonsensical? We're going to dive into a little math here. Now, I want to warn you people, this is going to get a little mathematical. So if you have any math phobes out there, you can take them out of the room now. We don't mind. Go get some caffeine or something, because we don't want your brains to implode, okay? Because you have to deal with math sometimes. It's just a reality of dealing with these topics. So we're going to just kind of dive right into it, and then we'll let these experts here kind of explain the details. But let's go to the next slide. Yeah, well, you do, right? I mean, you got to have some math and physics, right? It's just
math phobes. That's a good term.
Math phobes. Yeah. We have a lot of math phobes. So the Hartle-Hawking state basically is the conditions for the no boundary proposal that we're going to be talking about. Basically, what he hypothesized, what would happen if we can eventually rewind the universe to t = 0? Now, that's just given the assumption that, time is some kind of ongoing thing. We have an arrow of time, which is based upon entropy. The arrow of time is considered to be the difference between entropic states from lower to higher, because we all know that the universe is increasing in entropy. And they basically hypothesized what would happen if we just kind of rewound the universe. And as Landon pointed out, does it get to a mathematical singularity, or kind of get to a boundary condition where we don't have that singularity occur? Because we all know by now, general relativity breaks down at time = 0, right? General relativity can't really model what happens at that singularity. Now, you can evolve things like called loop quantum gravity to help do that, which the no boundary proposal, as far as I understand, kind of does. But loop quantum gravity and general relativity don't play well with each other. They don't like each other. So they're kind of incompatible as it stands now. Would you agree that's kind of a fair summation?
Yes, I'm going to point out what do you mean by not compatible is that you'd have to go from, if you said loop quantum gravity is reasons, you have to say, well, how do you go from loop quantum gravity to general relativity? Right, because we see general relativity is measured, has been measured and well confirmed multiple times, directly and indirectly. So how would you go from a loop quantum gravity did it to we have general relativity today? That's probably the bigger hurdle you'd have to overcome.
Everybody else agree?
Yeah.
Okay.
Oh yeah.
And so this is kind of describing the conditions to the Planck error, prior to the Planck error. Planck error ended 10 to the negative 43 seconds, I think, wasn't it? We're going to go with that.
Yes, that's usually a long time unit. Yes.
Okay.
Yes.
Next slide. Okay, so I wrote this, and I'm going to run it by you guys. This is how I kind of look at it, and you just have to tell me if this makes sense to you all. The way I look at it, for quantum loop gravity versus general relativity thinks space-time is more of a four-dimensional, what's called Minkowski space. Basically, space-time is integrated. There's a manifold, so to speak. Where you have, opposed to a neo-Lorentzian model where you have three spatial dimensions with one time dimension. In each case, space-time is malleable. We know that it can basically have deformation because that's all gravity is, mass, deforms space-time. We also think they can actually rip, what's called the big rip. But there's not a preferred frame of reference in general relativity. That means that wherever you are, that's your preferred, that's your frame of reference, but there's no preferred frame of reference to the entire universe. So there's no such thing as absolute time. One of the things that they talk about is relativity of simultaneity. So if you have two events that are spatially separated and they occur at the same time relative to a frame of reference to the observer, but they're not absolute, such that from different frames of references, they would actually see one event happen prior to the other one. How do you guys think that kind of relates to the well, what I just made makes sense, first of all?
Oh, yeah.
Yeah, it does make
sense.
So I'm
not way off enough field. Athena, go ahead.
Yeah. Well, that definitely, makes sense just coming from like a more of a basic observational standpoint, as opposed to diving in deep with anything. Because I know we're about to do that. But just looking at things like
I'm simple. I'm a simple man.
And I usually I work with kids a lot of times at museums, so that's kind of how I break down my science. But yeah, so when you think about that, exactly what you just said obviously makes sense because you think about it and you think about like, when you look at things from two different perspectives or whatever it is in the universe, one thing might be observed at a different time than another. Perfect example is the International Space Station. It's traveling a bit faster than we are. So they're actually aging a little bit slower than we are. So they see, Earth traveling at a certain rate, but then we see it traveling at a certain rate. And if you expand that into a much broader scheme of things in the universe, something much, much further away, like a rocket ship, and this is just talking about like time dilation, and you take two atomic clocks and you synchronize them, and then you put one on the rocket ship and one here on Earth, it's going to see our clock ticking much slower, and eventually might stop ticking because it's moving maybe at the speed of light. It's moving much faster than we are. And its clock is going to still be ticking at normal rate. So it can do a full loop around something, let's say sort of like a black hole, for instance. It can, if it for some reason can loop around a black hole and not get pulled in by its gravity, it may be traveling at about twice the speed that we would be traveling here on Earth, which means that people there would be aging at about half the rate that we'd be aging here on Earth. So what you kind of just said, and that's tying into a little bit different. That's more about special relativity, but yeah, it's something that it has been calculated. It's been observed. We've actually done experiments about this. So that's
these are confirmed things. Yeah, the relativity is confirmed. No matter what anybody tells you, it works. Yep. I'm a scientific instrumentalist, not a realist. I think maybe we might have some scientific. I think what they call them. What do you call yourself, Dr. Kroon? You're not an instrumentalist, or what are you? A scientific what?
I don't know. We didn't. You had to.
Yeah.
You had to.
We have to finish the discussion. Yeah, we didn't finish it. But what'd you call yourself? You had a term I hadn't heard before. A scientific coordinatist?
Hold on. I can go back to
he made up a term, and I liked it.
It made sense at the time, like in my defense.
Yeah, no, I liked it. It was a good coinage, actually. I didn't know what he was talking about. I've never heard this before. He's like, I just kind of made it up. But I was like, it works.
I want to know what it is. What is it?
Yeah, I don't know what it is, but it sounds really good.
Okay, so while he's looking it up, one of the things that you're talking about in terms of measuring, she was talking about time dilation, right, and time slowing down. One of the things that's going to happen, there's a space probe called the Parker Space Probe that people focus on. It's going to get really close to the sun, do these flybys to the sun to observe conditions now near the surface of the sun. But one of the other experiments it's going to be doing is another test of general relativity. I don't know if you know about this, but when the Parker Space Probe is at its maximum speed, where it's closest to the sun and zipping around and at its spot, it will be traveling close to 700,000 kilometers per hour. So that's about 430,000 miles per hour. That's a very non-trivial speed. And we are going, it has, the space probe has clocks on it for synchronizing events and sending out signals. And we're going to watch from our standpoint, this clock zip around near the sun. It's going into a more intense gravitational field, and we'll see time literally slow down for it, right? It will, time will run on that spacecraft at a slower pace than what we see here on Earth, and we'll actually measure that to a very fine degree. Yes, with respect to us.
We have to know with respect to us. If you're on that time, if you're on the probe, you wouldn't notice a difference.
Spacecraft, we'd
be actually running fast.
Everything.
Yeah.
Yes, and so you look back on the universe. But anyway, that's something that's going to be tested very well.
And
by the way, I found
it. What was it called?
Yeah.
What did you call it?
So I'll read you the little blurb I had. I said, am I a realist, a pragmatist, a scientific rationalist? There's probably a term for me. I think that third one is it. Does that sound familiar to you, Steve?
No, I think you said because I asked like a scientific compatibilist or something. Because I asked if you were instrumentalist or a realist, because a scientific realist would take a scientific theory and say this is actually the way the universe is, and a scientific instrumentalist just says, you know what, it doesn't matter whether it is or isn't. We can use it to model.
Here we go. So I scrolled down more. You said that you're an instrumentalist, and I said, I'm kind of both. I'm what I might call a circumstantial instrumentalist.
Circumstantial, yeah, that was good.
And I could think of scenarios that unambiguously conform to either paradigm, and then I said I'm a mutant.
Yeah.
LOL.
But
that was actually
good. Never assume that the universe gives a damn about your theory. That's one of the things my advisor kept hammering in on saying.
That's why I can't. I can't adhere to scientific realism.
It's very important here. The universe does not ask your permission to do what it does. So your
There
theory does not tell the universe what to do. Your theory is you make a theory in order to try to predict what the universe is doing, and we accept or reject your theory based upon evidence, based upon observation, right? That's
so your theory just
observable, which
it doesn't prescribe the way the universe must be.
Yeah.
Which is why the string model does not deserve the word theory at this point.
Yeah.
Well, I don't know. I mean, I'm kind of still reading the Cosmic Landscape, but as a mathematical, they call them theories in mathematics because the mathematics works for string theories, from as I understand.
Well, mathematics would be a model.
But we're gonna dive into string theory. We're gonna be here another 5 hours.
What is this math theory thing?
What is this math we're talking about? Real quick, I was gonna say something else. Oh yeah, Athena, it's funny you mentioned time dilation and all that, because this episode was originally going to be just me and Dr. Kroon, I think, and probably Landon, but I don't know if he was going to be available this week. But it was either this weekend or last weekend. Last weekend, I think it was. We were going to talk about time dilation and how neurons show us that time dilation works, but we'll save that for another time. But next slide. But it's so funny you mentioned that because we were going to do a topic on that.
What are the chances? Yeah, that's funny. Cool.
All right, key points of general relativity. General relativity, the way I describe it, is it basically models the shortest geodesic path between two objects. So it's kind of like a straight line for curved space. General relativity holds time as emergent from three-dimensional space-time curvature. This is due to energy distribution. So general relativity really kind of thinks that time is an emergent property of space, and that's kind of a critical thing. And that general relativity maintains a classical trajectory between 2 points. So if we wanted to get from A to B, we have to go through what we would call normal space-time, and that is the shortest distance for us, even though if you could actually like do a wormhole or something like that, you could theoretically make a shorter distance. Just like if I could tunnel my way through the Earth, I can get to the equator faster that way than I could going around the circumference, right? So that's kind of the key points for general relativity. Simple, but want to add anything to that, anybody? Or is it pretty basic?
Hit the nail on the head there.
There's always that thrifty saying that goes, matter tells space-time how to curve, and space-time tells matter how to move. That's always we can't have a discussion of GR without that little thrifty turn of phrase.
As you can tell by the diagram, the sun is the body of mass, and it tells space-time how to curve. You literally are following the curvature of left of that potential energy well of the sun. Now, this is only a two-dimensional cross-section. Remember, people, this
by
is
the
actually...
way, that diagram is not curved to scale.
No, it's not curved to scale. Thank you, Landon. People were kind of concerned about it, I'm sure. All right, next point. This is where we start getting into the fun stuff. So this is some of the key points of quantum loop quantum gravity. So what it usually is called the path integral formalization, and I'm going to have one of you people talk about it here in a second. But the PIF is basically a way to calculate every possible trajectory between 2 points and find the likely path between A and B for which a trajectory was taken. Now, the path integral formalization is literally based upon wave functions, and that a particle will take all these different paths, but as you measure something, then it actually manifests only one path. But it's actually existing in all these different paths simultaneously, which is something weird in quantum, being in multiple places at the same instant. But what it actually does is it looks at every single infinite amount of paths you can take from A to B, and basically has a formula that says all these paths are taking at the same time. That's the way I'm kind of looking at the path integral formalization. I know all three of you have talked about this before, so who wants to kind of jump in on this first?
Landon,
you'll take forever.
Start?
So, Landon, go ahead. I'm just kidding.
Well, I mean, I know that Feynman did a lot of stuff with path integral formulation, and I remember him